Glass Part 2, Manufacturing for Performance. Today, glass is selected from a wide range of products that meet different criteria for functionality and performance. In this course, you will learn about 3 types of glass: float, rolled, and coated. By definition, glass is a uniform, amorphous solid material and is usually produced when a suitably viscous molten material cools very rapidly to a point where molecules have very little mobility. In its pure form, glass is a transparent, relatively strong, hard-wearing material, which can be formed with very smooth and impervious surfaces. The architectural glass found in most buildings today is commonly referred to as float glass. Float glass consists primarily of silica sand, soda, and lime. Float glass can be clear and virtually colorless, or tints can be added during the manufacturing process, which reduces visible light transmittance as well as solar heat gain. In North America, the most common glass substrates can be placed into 3 categories based on their effectiveness to control solar energy. Click each button to learn more. High solar transmittance float glass products absorb little of the heat energy from the sun, which means that they provide little protection from solar heat gain and potentially damaging UV and visible light. They do offer excellent clarity and color neutrality, important for many applications. Medium-performing substrates provide more protection against solar heat gain and visible light transmittance and feature color. The highest-performing float glass products provide excellent protection against solar heat gain as well as high levels of damaging light transmission and are heavily colored. Click each button to learn more. Float glass consists primarily of silica sand, soda, and lime, referred to as the batch. These materials are digitally weighed and mixed with cullet or crushed recycled glass, as well as small amounts of other materials, then transferred by conveyor into the batch house. The batch is continuously fed into the furnace, where it is melted. In the furnace, the batch is heated to its melting point, approximately 2,800 degrees Fahrenheit. The molten glass flows to the end of the furnace, where it moves through a canal onto a pool of liquid tin. As the glass moves over the liquid tin, metal knurls contact the glass ribbon at its edges, helping to control both its width and speed. The speed at which the glass ribbon moves will determine its ultimate thickness. Because tin has a higher specific gravity than glass, the molten glass floats and forms a perfectly flat layer. The glass must be cooled to approximately 1,100 degrees Fahrenheit before it can be lifted out by rollers. As the glass ribbon is pulled over the liquid tin and before it is lifted out onto rollers, reflective or low emissivity coatings can be applied to the atmosphere surface of the glass to improve its ultimate performance in a building. This coating process is referred to as chemical vapor deposition, and these coatings are known as pyrolytic or hard coats. Lifted out by rollers, the glass ribbon finally leaves the tin bath. Now it is cooled slowly or annealed to remove any residual stresses and make it stronger. After annealing, the solidified ribbon of glass is sufficiently cooled enough for processing and can be cut into pieces. Cooled glass passes through inspection booths to ensure that it has the uncompromising quality needed for its end use. Defects are marked and the rough edges, where knurls pulled the glass through the molten tin, are trimmed for use as cullet in a future batch of float glass. The remainder of the glass ribbon is cut for packaging. Float glass can be cut into large standard sheets or cut to size according to its ultimate use. The glass is then inventoried and ready to be shipped. A glass substrate is float glass without a coating. Substrates can be grouped according to their level of solar transmittance, which relates to how much energy from the sun passes through them. Typically, a substrate by itself has relatively low solar and visible reflectance, but its transmittance will vary. Substrate appearance is affected by thickness. Since the color of the substrate is in the material, as the substrate gets thicker, it will appear darker. Coatings can be combined with substrates for various effects in both performance and aesthetics. Perfect for many architectural applications, Rolled glass begins as a molten glass, which is processed through a set of 2 engraved rolls that apply a pattern to the glass as it passes through them. There are endless possibilities when manufacturers develop attractive patterns to roll onto the architectural glass. Patterned glass can be used for interior and exterior decorative elements, especially in heavier glass thicknesses, including storefronts, foyers and vestibules, interior partitions, railings, and translucent window and door treatments. Rolled glass can also help channel or direct visible light energy to be used in lighting panels, including solar or photovoltaic cells. To further improve the performance of glass, manufacturers have developed coatings that can be applied during the float process or as part of the finishing process. Click each button to learn more. Hard or pyrolytic coatings are applied during the float process and become part of the finished glass itself. Soft or sputter coatings are applied through a magnetic sputter vapor deposition process, separate from the float glass process. Reflective and low emissivity coatings offer excellent solar control, minimizing heat gain. Not only are architectural coated glass products increasing in sophistication, but manufacturers and fabricators are creating complex new approaches to applying them in the most effective manner. Glass surfaces are numbered, with number 1 representing the exterior or weather surface of a glass panel or insulating unit. Low emissivity or low E-glass coatings are metallic layers applied to float glass. Emissivity is a measure of a material's ability to re-radiate absorbed infrared radiation. Low emittance glass blocks a significant amount of radiant energy and reflects it back toward the source. Low E coatings can be applied to both sputter and pyrolytic coating processes. They can also be spectrally selective, allowing for the use of passive solar energy in cold climates. Like reflective coatings, low E coatings help to significantly reduce solar heat gain and maximize energy use, but without a reflective appearance. To maximize the performance of low E coatings, there are some general guidelines. The U factor is the same whether low E coatings are placed on surface number 2 or number 3. The SHGC is generally lower with low E coatings on surface number 2. Thermal stresses may be more common when the low E coating is on surface number 2 rather than on surface number 3, especially when using tinted exterior lights. This may require special consideration to avoid breakage from the added thermal stress. Pyrolytic coatings are metallic oxides applied during manufacturing, as the glass ribbon is pulled over the liquid tin and before it is lifted out onto rollers. Because these coatings are a permanent part of the glass itself, they are extremely durable and tough, hence the common name hard coating. They can also include low emissivity, energy-efficient coatings, and reflective solar control coatings. Glass products that feature a pyrolytic coating have a number of advantages. They are easy to handle, transport, stack, and store. They can be heat-treated and laminated to meet specialized applications. Pyrolytic products are durable enough to be used monolithically. Consult with the product manufacturer for details. Pyrolytic coatings can be exposed to weather positioned on the number 1 surface, but this is not recommended as the coating may be easily damaged. Sputter or soft coatings are applied through the bombardment of metal atoms onto the surface of float glass. This process is known as magnetic sputter vapor deposition. These sputter coatings are less durable than pyrolytic coatings. However, they deliver a wide range of benefits. Sputter coatings are versatile. They can be applied to any glass substrate and cover the full range of performance and aesthetic requirements. There are literally hundreds of sputter coating possibilities. Sputter-coated products feature new post-temperable technologies that allow them to be heat-treated. Reflective glass coatings are metallic layers applied to float glass in order to reflect short wavelength solar energy back into the atmosphere, therefore reducing solar heat gain. They also provide a distinctive appearance for architectural facades. Highly reflective coatings absorb the largest portion of direct solar energy not reflected. This is a disadvantage, as the glass gets very hot. Reflective coatings can be applied to glass substrates by both pyrolytic and sputter coating processes. Pyrolytic reflective coatings are designed to be used on the number 2 or number 3 glass surface, but are durable enough to be installed on the number 1 or exterior surface. Soft reflective coatings must be applied to the number 2 or number 3 surface, as they cannot be exposed to weather. Benefits of reflective products include significant reduction in solar heat gain, making interior spaces cooler and more comfortable, lower capital costs needed for air conditioning systems, reduction in ongoing air conditioning expenditures. There are some guidelines for viewing coated glass products. The best conditions are outdoors in natural light, both sun and shade. When viewing a building from the exterior, observers will see a combination of reflected light and transmitted light. For reflective glass, most of the light reaching the observer is reflected from the coating, and there will be little read-through. Reflective glass should be viewed in a vertical position against a dark background. For low E glass, there will be a lot of transmitted light, resulting in significant read-through. Low E glass should be assessed in a vertical position against a medium or dark-colored background, depending on the specific glass. Congratulations! You are now familiar with the 3 types of glass generally used in fenestration products. Plus, you've learned how they're made and how each can most effectively be used.